Hello again. As I promised you, I'm back with the same problem that in the previous video, I determined the speed at B. If you guys recall, the weight of this bar was given to be 2 pounds, right? And it started with a speed of 5 feet per second. As it passed position B right here, we ended up getting velocity at B to be 34.1 feet per second using the principle of work and energy and specifically conservation of energy. Now, what I want to continue with this problem and determine is what would be the normal force exerted by this curved rod to the slider, the 2-pound slider. So we're going to call that normal force, and also find the rate of change of speed. Now you know that the rate of change of speed is known as the tangential acceleration. So clearly I want to use the NT coordinate system here. So actually this guy, if you draw a tangent, it's not vertical, or at least we don't know if it's vertical, but it turns out that it's not vertical. So tangential axis and perpendicular to that would be the normal axis. So let me go ahead and draw a free body diagram for you of this bar at this instant. We can actually draw the free body diagram right here on this picture if we could. So what we want to determine is this normal force here, N. I'm going to call it N. Remember, the weight is 2 pounds. We already know that. And there is also, let me actually move this N down here. And keep in mind that we also have the force of the spring here. So when the spring is here, right, remember that the force of a spring is going to be K times S2. Remember, it's 10 pounds per foot, right? And if you guys recall, the undeformed length of the spring was 2 feet. So since the length is 3 feet here, so that means this spring is stretched by 1 foot. So actually the force of the spring would be 10 pounds. I advise you to go and see the previous video where we have all that information. So now we know that the force of the spring here is 10 pounds. Since it is stretched, so the force is going to be to the left. So that's 10 pounds. So basically we got this normal force, which the way I drew it as if it's pointing that way. So this is the normal force, right? You got the force of the spring and you got the weight. All right. Now, what we need to determine, guys, very important, is this angle. Because besides this angle, we won't be able to do the problem. So that angle can be determined by calculus. See, we have the profile of the path right here, y equal 4.5 minus 1/2 x squared. So if you go ahead and take the derivative of that, that becomes minus x. And if you plug in the value of x, which is 3 actually, so that becomes -3. As you know, derivative is slope of the tangent line, so that should be tangent theta. If you solve for the angle, actually, it should be about 71.57. So we have that angle. So then we can break these components, along the normal and tangential direction, specifically the 2 pound and the 10 pound. Because clearly n is along the normal axis. Okay, one other thing we need to determine is the normal acceleration. Normal acceleration is v squared over rho. In the previous problem, I calculated actually the speed based on conservation of energy for you. It's 34.1. Well, what about radius of curvature? You guys recall that the radius of curvature can be determined using this formula. At that specific location. So actually, if you plug in, remember the y prime was -3 squared raised to power 3/2, and y double prime, by the way, becomes just -1. So if you go ahead and solve for rho comes out to be about 31.6 feet. So now let's go ahead and calculate the normal acceleration, which is v squared over rho. So that would be 34.1 squared divided by 31.6. and that is about 36.77 feet per second squared. So that's actually the centripetal acceleration, this acceleration pointing this way toward the center of curvature of the path. So unfortunately, I'm running out of space, so I have to move to the next page. Let me redraw the free body diagram in the next page, actually cleaner than the way I have it here. So let's go to the next page, and then let's draw our tangential axis and normal axis, more or less. This is the tangential axis, this is the normal axis, let's say. This was the weight of the object, right? So this is the slider here. The weight was 2 pounds. Remember, the force of the spring was 10 pounds. And we wanted to find this normal force and the rate of change of speed, which is the tangential acceleration. And remember that this angle, theta, was calculated earlier, and it was 71.57. Okay? So basically, and we just calculated normal acceleration based on the velocity and the radius of curvature, and that came out to be 36.77 feet per second squared. So we are ready to go. Apply the equation of motion in the normal direction and say it equal to mass times normal acceleration. Now remember that this is your positive normal as shown, right? This direction. So